Hey,
Hey, how's it going?
pretty good. How about you?
Doing all right?
How's Tomas doing?
What was
I
that?
mean, he's done. I mean, he has given his thesis to the committee, and he's done. I mean,
Well, still have to present though, right? Which I feel like it's not.
well, but this is just typical, right? I mean, just an hour, give one more talk. That's how I think about it. Aren't you thinking about the same, Makoto, or do you think it as the great reveal of your work?
I mean, I feel like there's a bit of pressure, isn't it, to like do a better talk than your usual.
No,
I mean, there's more. I feel like there's gonna be a bigger audience, right, than your usual talk. So, like,
well, not
right? Yeah.
you mean except for your family or your friends, or you mean except for this, or
No, just like your friends and families and other grad students, right? Too. I think.
I see.
Well, maybe I'm just arrogant. Maybe I'm just assuming that people will show up. Maybe people are not gonna show up, and it's just gonna be like a regular regular grad student talk or something.
I actually don't know because with Zoom things are weird. I mean, if it was like an actual this defense, like in person with this defense, you would expect some people to come. But now with Zoom, it's either easier or harder for people depending on how they feel about Zoom, right? I think you're muted.
It's either it's either easier or harder, right, Menzel?
I mean,
One of the two.
I think it depends on the person, right? If you like Zoom, it's easier for you. But if you hate Zoom, it's hard for you, right? And there's no in between with these things. I think with Zoom.
Someone likes Zoom? What?
I mean, some people don't mind, being on Zoom for like 8 hours straight, but some other people do mind, right?
Oh, I just feel like it's just all those hours are taken from my life. Like one day I'll be old and I'll just be like, well, death is much nearer now because of all those hours that I spent on Zoom. But anyway, you got to do what you got to do. Are there any questions? Okay, I guess we continue. So I realized this lecture is a little bit fragmented because I was trying to work around talking about cohomological dimension of profinite groups, and then eventually I realized that I should just talk about it. And so I don't know. It might be too late for that to be a Friday lecture, or maybe I just didn't do a good enough job. So maybe someone could still come back and do it. But yeah. So in today's lecture, I want to talk quickly about well, that doesn't look very good, about cohomological dimension of profinite groups, and then I'll talk about Brouwer groups. I think I just defined it last time, and that was all that I did. And I'll have to check, but I think we may actually be ready to start talking about local fields in the following lecture. So that's good. Okay. So yes, remember we've already defined the cohomological dimension of a discrete group. It's just the maximum index of non-vanishing cohomology for any and all modules over that group, taken forever, the supremum of such indices. And so yeah, so this is a reasonable profinite analog. There's just a couple of things. First of all, we do it prime by prime. So whatever the definition is, you see that for a profinite group, there's going to be a cohomological dimension at P for a given prime number P. And then the actual cohomological dimension is just going to be the supremum over all the cohomological dimensions at P. And then the other question, I guess, is, well, what kind of module do we want to, do we want to restrict to? So probably we should restrict to discrete modules, right? Because that's the category that we've been working in. So yeah, you might have expected the cohomological dimension of a profinite group just to be defined as we did cohomological dimension for discrete groups, but restricting to discrete CG modules. And so our definition is actually restricting to a somewhat smaller class of modules than that. the thing I was just alluding to is closely related to something called the strict cohomological dimension, which if we need it, then I'll define it, but I'm not defining it in this lecture. So anyway, so the matter of it is that the cohomological dimension at P is kind of what you think the only G modules that you allow are, one way to say is that they're discrete and also torsion. That was kind of what you might not have expected. And then you, well, you only look at where's the P come in? You only look at the P primary torsion of the cohomology vanishing. But then if you think about it, if the module is torsion anyway, then you could put the P prime, that any torsion module is going to be the direct sum of its P primary torsion modules, and cohomology commutes with direct sums. And so in fact, I could have just restricted, instead of putting the P primary torsion on the outside, I could have only restricted to P primary torsion discrete G modules. Okay, so those things come to the same. Okay, so the cohomological dimension at P is the largest non-vanishing that a torsion G module can be, that a P primary torsion G module can be. Okay, and so and infinity if there is no such a guy. And so here's a very simple example. So what if the group is just Z mod LZ, right? And you look at the cohomological dimension at P. And so it just as an easy consequence of the definition, I mean, because here this is if you have a finite group, then all the higher cohomology groups are torsion of the order of the group. So certainly the L torsion of certainly the P torsion for any P different from L of all these cohomology modules for this group is going to be equal to 0. And so that's why that's true. And then if you look at P equals L and you just go with what we already knew, I mean, this is after all a finite group, so it is the cohomology as usual. And if you go with what we know about finite cyclic groups, then you'll find that the cohomological dimension is infinite. Okay, so that's just a first example. And then if you want to continue this example, if your profinite group is actually a non-trivial finite group, then it's not so difficult exercise. It's easy to see that the cohomological dimension, the P cohomological dimension is going to be 0 unless P divides the order of the group in general, unless P divides the supernatural order of the profinite group. The cohomological dimension of P has to be equal to 0. And then if the group is finite, then the P cohomological dimension will be infinite for all primes dividing the order of the group. Okay. Well, so this is basically saying that the concept of cohomological dimension for profinite groups is much more interesting when the profinite group is infinite. But again, remember that for discrete groups, we also found that the cohomological dimension of a non-trivial finite discrete group was always infinite. Okay. So that's not so surprising. Okay, let's see. So what did I want to? Here's a theorem that I think I'm just the second theorem I'm going to prove. The proof is not very hard, and the first proof I'm just going to state and skip the proof. So right. So if I have a profinite group and I have a prime number, the following are equivalent. The P cohomological dimension is less than or equal to n. The second one, this is what I was already saying this before, so the equivalence of 1 and 2 is quite easy. That if you only take cohomology of P primary torsion discrete G modules, then that should vanish for all indices greater than n. And so it's the third one that's a little bit more interesting. So the idea of the third one is that we're trying to check whether the Qth cohomology or the cohomology in indices greater than n vanishes for all discrete P primary torsion G modules. Well, but there's a lot of discrete P primary torsion G modules out there. There's a lot of numbers bigger than n. like infinitely many. And so part 3 says that you can check much less. So in order for the cohomological dimension to be less than or equal to n, it's sufficient to look at n+1. Okay, that's not so surprising. And then in addition to being discrete and p-primary torsion, you can assume that it's simple as a ZG module, which of course means that there are no proper non-trivial G submodules. Okay, so that's simplifying things considerably. Okay, and so yeah, I think 1 is equivalent to 2 is kind of, I was saying that before actually, I think it's almost obvious. 2 implies 3 is immediate. I'm just going from a stronger condition to a weaker looking condition. And so the matter of this is that 3 implies 1, and I'm skipping the proof of that. Somebody could still decide that they want to give the proof of that. Okay. And so then this is where things get a little bit, this is some indication of why it's nice to break down the cohomological dimension prime by prime. There's this result and then I think another result later on the page. But the cohomological dimension of pro-P groups is so much easier to check. So it can't get any simpler than this. The cohomological dimension at P is at most n if and only if the n plus first cohomology of just Z mod PZ with trivial G action is equal to 0. Okay, and so again, the left to right is of course immediate. And it's at first, it's really pretty surprising that, again, a priori, from the perspective of 2, we were supposed to check that all the cohomology and indices greater than n of all p primary torsion discrete G modules was equal to 0. Okay, so first of all, it's enough to check it in dimension n+1. That's not so startling, but yeah, really all we have to do is check this one cohomology group vanishing, and that tells us the cohomological dimension. Right? And so therefore, of course, you can compute the p cohomological dimension of a pro-P group in terms of the largest non-vanishing cohomology of with coefficients in Z mod P. Okay, so so again, left to right is no problem, and let's do right to left. Much of this was already hidden in checking this, and so if you believe this previous theorem, I'm so sorry that I crossed out a bunch of stuff there. I'm supposed to show that if I have a discrete simple G module P primary torsion, then the n plus first cohomology with coefficients in that is equal to 0. And so yeah, so say the way that I'm going to prove this is in a kind of funny way. I'm going to show, it's also enough to show. We can also assume that A is not equal to 0 because, of course, if A is equal to 0, then they're all equal to 0. So the way that I'm going to prove this is actually going to say, right, so I know that this one non-vanishing is equal to 0, and this one A is, I know that for A equals Z mod PZ, the n plus first cohomology is equal to 0, and according to this theorem, I'm supposed to deduce that the n plus first cohomology of any simple P primary G module is equal to 0. Okay, I guess, 0 is not a simple module, so fine. All right, and then the way that I'm going to prove this is actually that Z mod P with trivial G action is the only discrete simple P primary G module. This is calling back to what I was saying in a recent lecture about how representation theory of P groups and characteristic P is totally different. And this is kind of like the only irreducible FP of G module is Z mod PZ with trivial action. That's more or less what we're saying here. It's closely related anyway. Okay, so yeah, so that's what I'm going to prove. So if I take a non-zero element of my simple discrete P primary G module, so since the G action is continuous, as we've seen before, it acts locally through a finite quotient. So it acts on X via a finite quotient. So the G orbit on X is finite. And so then you take, so how do you get the ZG module generated by something? First, you take the G orbit, then you take the subgroup generated by it. So the G orbit is finite, and then I take the subgroup generated by it, and so I'm going to get a finitely generated torsion group, and so therefore a finitely generated torsion Z module is going to be finite. Okay, so the ZG module generated by this guy is going to be finite. Well, since it's simple, then it must be equal to the Z, I take any non-zero element, it's going to have to, the ZG module generated by it has to be the whole thing. That's really what simple means. And so therefore the whole guy is finite. And therefore, again, we really reduce to the case where G is a finite P group, because the action of a profinite group on a discrete module is locally factors through any finite quotient, but the whole module is finite. And so therefore, the whole thing factors through a finite quotient. And again, remember, here's now our sort of positive characteristic representation theory fact. Recall that whenever you have a finite P group acting on a P primary torsion module, as long as the module is non-zero, its invariants are non-zero, okay? But again, it's supposed to be a simple module, and the invariants are certainly a ZG submodule, and so therefore the module is equal to its invariants. In other words, the G action is trivial. Okay, so what are the simple finite commutative P groups? Yeah, it's just Z mod PZ. That's the only finite simple commutative P group. Okay, so it does follow that the only simple P primary torsion G module is Z mod PZ with trivial action. Okay, so that's the end of that. Yeah, so this suggests that there's a much nicer theory of what am I trying to say? It's worth studying the cohomology of pro-P groups for its own sake. It's a lot nicer. And then the next fact that, again, I'm going to skip the proof of, so someone might want to do it. This is also very important, is justifying, is also explaining the importance of pro-P groups in the theory. So if I take a profinite group and I take GP to be a CeLO P subgroup of G, now already I'm kind of slipping something under the rug. So what do I mean by a CeLO P subgroup of a profinite group? Okay, and so you have to, work out for yourself or look up the fact that such things exist. So there's a essentially, just by passing to the inverse limit on the standard CeLO theory of finite groups, you get a very similar looking CeLO theory of profinite groups. So, okay, by definition, what is a P-CeLO subgroup of a profinite group? Well, GP is a pro-P group, pro-P subgroup of G, and it is maximal among pro-P subgroups of G, which you show is equivalent to showing that the supernatural index, which also makes sense. If you have any closed subgroup, you can define a supernatural number, which is the index of the subgroup, which is just like the LCM of the indices of the open finite index subgroups, which contain the closed subgroup. And so again, part of CeLO theory is that you will have a maximal pro-P subgroup if and only if the profinite index is supernatural index is prime to P. And the rest of the CeLO theory goes through. Okay, so again, CeLO P subgroups exist. Every pro-P subgroup is contained in a CeLO pro-P subgroup, and any two CeLO P subgroups of the same profinite group are conjugate. Okay, so there really is a pro-P CeLO theory, and it's nice. It's not profound. It follows pretty easily from. It's easier to prove the things that I just said than it is to prove the CeLO theorems for finite groups. Okay, and anyway, and so then the nice result is that the P cohomological dimension depends only on the CeLO P sub. Okay, so you see that. As far as this is analogous to some other results we were seeing before, where we were kind of localizing at CeLO P subgroups of finite groups and seeing that that they kind of controlled a lot of the cohomology of the group. Yeah. So the cohomological dimension of a group is really local in the group theoretic sense, that it only depends upon its CLOP subgroups. Okay, so now I want to do an example. So this is either screwing up or helping you do an exercise that's going to come like on the next page. And this is a kind of funny example because it sounds good until the very end, and then you're going to realize that you're going to have to go back and think more carefully about something. Okay, so I want to compute. So this, okay, first of all, I have a ZP and a Z mod P, right? So ZP is the p-adic integers, of course, the inverse limit of Z mod P to the NZ. And so I'm going to compute H2 of ZP with coefficients in Z mod P, which is relevant by this last result. I'm wondering what the P cohomological dimension of ZP is. Okay, that's why I'm doing this computation. So if this thing were to turn out to be equal to 0, then this is the, let's think for a second. H1 of ZP with coefficients in Z mod P is just Hom from ZP into Z mod P, right? So let's go over here somewhere. Okay, and well, what's that? Well, how do I get a homomorphism from any commutative group into Z mod P? It should factor through the it should factor through the co-kernel of multiplication by P, right? So if I have a homomorphism from any commutative group into a P torsion group, it's going to have to factor through. So this should be Hom. What am I trying to say? I'm trying to say that that PZP has to go to 0 under any such homomorphism, clearly. So this should be the Hom from ZP PZP into Z mod P. Okay, well, what is ZP mod PZP? I'll wait.
It's just Z mod PZ.
Yeah, okay, good. And what is this Hom? Well, I have to send one somewhere. I'll wait. Someone better say it. I got all day. Maybe we'll be here until 4 o'clock.
Z mod P to -1.
Oh no. Oh no. I'm gonna wait till someone says it correctly.
Or sorry, Z mod P.
Yeah, Z mod.
Yeah, you have the trivial one.
Yeah. Okay. So you see that. So the H1 with coefficients here is a one-dimensional Z mod P module. Okay. I mean, I guess maybe, yeah. So now, I mean, maybe I want these Homs to be continuous for the. In general, I want these Homs to be continuous for the profinite topology here and the discrete topology here. But in this particular case, that was automatic. Anyway, and so you see that this was not 0. Okay. So if we're trying to compute the cohomological dimension of ZP, well, again, at every prime L different from P, the L CELO subgroup of ZP is most certainly 0. So the cohomological dimension of anything other than P is certainly 0. And then this little computation over here said that the cohomological dimension is bigger than 0. Okay, because if it were 0, then all the Chi are cohomologies. Now let's look at H2. Okay. So yeah, most of this is obvious, and then the end is kind of surprising. So again, you know, as for all Galois cohomology, you can compute it in terms of limits from finite group cohomology. And so ZP is the inverse limit, and that comes out as the direct limit. Okay, you have to You have to, if at one point you may want to stop and think about what the maps are, but it's certainly true. And then you say, okay, I see how this goes. We know everything there is to know. We have formulas for the cohomology of finite cyclic groups. There's a twofold periodicity. So that should be the same as Tate H0, okay? And now Tate H0 is what the invariance? Well, it's trivial, so it's Z mod P modulo the image of the norm, okay? But so the action is trivial, so the norm, right? What is this going to be? The norm is going to be it's going to be it's the sum over all the elements of P to the NZ, but they all act trivially. So the sum of all of them is really the norm map is just going to be multiplication by P to the N on a trivial module. I didn't write that down, but if you think about that, that's what it is. So the norm map is multiplication by P to the N, but P to the N is certainly 0 on Z mod P, okay? And so therefore the Tate H0 here is Z mod PZ because the norm map is 0 anyway. And so the answer is that whatever this cohomology group is, it's the direct limit of Z mod PZ. Now you might think, if you weren't paying attention, you might think that the direct limit of Z mod PZ is Z mod PZ. No, it's 0. What in the world is happening? Well, the direct limit doesn't just depend on the groups, it depends on what the maps are. Okay, so you have to go back and you have to convince. Here there was a, by equal, I mean a canonical isomorphism between the H2 and the Tate H0. And then you have to ask yourself like what these transition maps are. And so Harari makes a remark about this, which I'm referring you to, remark 4.2.9. The transition maps here on the Tate H0 for a cyclic group, finite cyclic group, are the transition maps are given by the norm map. And again, the norm map is going to be 0 in this case. And so this is I don't know. There's a good moral here. You can't just write down inverse limits and think it all works out. In order to compute an inverse limit, the transition maps really, really matter. And this time the transition maps are the norm maps. And so it is what is from each Z mod PZ to the next Z mod PZ, it's the 0 map. And therefore the inverse limit of Z mod PZ with the 0 map from one to the other is equal to 0. So that's okay. Read the fine print. Okay, but what did we conclude based on this? What is the cohomological dimension of ZP? Well, the cohomological dimension at some prime different from P was 0. And for the cohomological dimension at P, it's blah, 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 blah. It's the, we wait until we get a vanishing. It's 1 less than the index of the smallest index of a non-vanishing cohomology with coefficients in Z mod P. So what is it?
1.
1, yeah. Okay. And if you think about this, then so this is a basic computation. I guess I'll just say this will also compute. Therefore, also I'll write this. Therefore, what's the cohomological dimension of Z hat? Well, what do you think a CeLO P subgroup of Z hat is going to be? Well, just like for normal CeLO theory, any commutative group, even nilpotent, I don't need that, any commutative group is the direct product of its CeLO P subgroups. So Z hat should be the direct product of its CeLO P subgroups. What is Z hat the direct product of as we range over primes?
something like C, like N.
So- Yeah, go ahead.
It should be like N with infinity or something.
Well, so Z hat
Yeah.
is the inverse limit of Z mod NZ.
Yes.
And if I wanted to do a prime power decomposition here, so this would be the inverse limit of Z mod some powers of P.
Yeah.
And so if I just separate all the prime powers from each other, as I can do by the Chinese remainder theorem.
The p-adic integers.
Yes, yes.
There.
Right?
Yeah.
Okay. You guys are worrying me a little bit here. Yes, Z hat is the product, even as a ring. Z hat is a profinite ring. It is the product over ZP. Okay, and so it follows from this that the CeLO P subgroup, the unique CeLO P subgroup of Z hat is ZP. Again, the CeLO theory for commutative P groups is especially simple. Just everything canonically decomposes into its P parts. Okay? And so, what should the cohomological dimension of Z hat be? If for any group the P cohomological dimension is the same as the P cohomological dimension of any of its CeLO P subgroups.
It's 1 at every prime, so it's 1.
Yeah, so this exactly. So CD of P is equal to 1, of Z hat is equal to 1 for all P, and therefore the cohomological dimension of Z hat is equal to 1. So very, very good. It's very sort of shouldn't have written on that spot, but yeah. Okay. So that's very important. So you see that it's okay. So I mean, so Z hat and ZP are one dimensional in this reasonable sense. All right. Good. So now I will push back to talking about Bauer groups. And so we'll see that if you want to, soon enough, we're going to want to think about cohomological dimension. The cohomological dimension of the absolute Galois group of a field is very relevant to the study of the Bauer group of the field. Okay. So for a Galois extension L over K, I'm going to take the Brouwer group of L over K to be this, this kind of relative Galois cohomology. And then remember, by definition, the Brouwer group of K was Galois cohomology of the absolute Galois group with coefficients in the multiplicative group. So the multiplicative K-sep cross. And so therefore, with this terminology, the Brouwer group of K is the Brouwer group of the separable closure of K over K. And so the first proposition here is that this relative Brouwer group, in the sense, is also equal to the kernel of the natural restriction map. So again, remember, we defined whenever you have any field extension, we defined, that was like the first thing we did in the last lecture. We have this restriction map for an algebraic field extension. This is just, you know, it's clear that the absolute Galois group of L is a closed subgroup of the absolute Galois group. It injects into the absolute Galois group of K as a closed subgroup. So this is just the usual restriction to a closed subgroup. But yeah, no, so it's not obvious that this kind of Brouwer group with the automorphism group of L over K is, in particular, we're saying that this relative Brouwer group lives injectively inside the Brouwer group of K, right? And that's not a general fact about Galois cohomology, right? So let's prove this, sort of this. So if you take the longer inflation restriction sequence that I defined before, then you're gonna get this. Right, so we have the relative one inflates into the absolute one, restricts to the subgroup, and then we keep going in 2 dimensions. So again, this is this 5-term exact sequence, which I claim is coming, I said, you know, like it or not, it's coming from this Hushel-Tser spectral sequence. Okay. But in our situation, Hilbert 90 is telling us that all of the first 3 terms are equal to 0. We have Hilbert 90 even for relative Galois extensions. That's the way that we proved it. So yeah, and so all those 3 groups are 0. And so that tells us, well, what I was saying before, first of all, that that actually this relative Brouwer group here injects into the Brouwer group of K. Right, but so that's not everything that I said. So it's also, yeah, so therefore that it injects into it, but I claim that it should be the kernel of the restriction map. And for this, I'm just going to pull out a result that I don't think I've discussed yet. This is another consequence of the, if you have a spectral sequence and you have like more things vanish than you expected, then you can say a little bit more. So this, I don't think it has to be proven by the Hushel-Tser spectral sequence, but that's one way to prove it. Because the first 3 terms of the sequence, of this inflation restriction sequence vanish, you get a longer exact sequence, okay? And again, it's just a very, very, very basic fact. It's like kind of more homological algebra than group cohomology, really. But so trust me or look it up. Then you can extend, because the first 3 terms vanish, you can extend the inflation restriction sequence in this manner, okay? And so, well, what is that telling you? We already knew that this thing injects into this thing, and then the exactness here, when we restrict to L, is precisely telling us that, well, the image of this thing, which is the thing, because the kernel is 0, is the kernel under restriction, okay, which is exactly what I claimed. Okay, so it follows from some extra vanishing. So it follows from like a really long inflation restriction sequence. So if you have enough vanishing in low degrees, then you have more exactness in higher degrees. Okay, so this is a very important result. So this relative Brouwer group is actually the elements of the Brouwer group of K that are killed by restriction to L. Okay, that's certainly very useful. Okay, and so just as a quick comment, so for any field extension, we can define the relative Brouwer group as the kernel of this restriction map, as I just said. For any extensions of fields, we defined a restriction map in Galois cohomology. Okay, and this is actually interesting. It's come up in my work, not super recently, but some years ago in particular. So one case which is interesting, believe it or not, is if you take a variety over a field K, and then you take the Brouwer group of KV over the Brouwer group of K. So these are classes in the Brouwer group of K, which become trivial when you restrict them to the function field of the variety. Okay, and so I don't really have time to talk about this, but it's related to something that I brought up at the very end of the last course. Whether you can descend divisor classes. Okay, so every divisor defined over the ground field of a variety is in particular gives rise to a Galois invariant class, divisor class over the algebraic closure. The other way around is not clear and is in fact not always true. So if I have a variety over K and I look at it over the separable closure, and I have a divisor over the separable closure that is linearly equivalent to all of its Galois conjugates. Okay, that's what a Galois invariant divisor class is. Again, does that mean that it comes from a rational? Does it come from a rational? Is it the class of a rational divisor on K? Okay, so that's Galois descent for divisor classes. And in fact, there is in general a Brouwer group obstruction to doing that. Okay, and so the answer is that if this relative Brauer group of KV over K were equal to 0, then you always can descend invariant divisor classes, and conversely, every non-trivial element of the Brauer group gives you this relative Brauer group gives you an invariant divisor class that does not descend. Anyway, if you're interested in this, let me know, and I can refer you to some papers of mine and to some other people. But there's a Picard-Brauer sequence that comes in here. All right, which is also coming from the Picard-Brauer sequence is coming from some Leray spectral sequence in what you call it, Étale cohomology. Oh, okay, so it's a little. I mean, you could say it less fancily if you wanted. All right. So here's one more quick but useful prop. So if the characteristic of your field does not divide some positive integer n, then the n torsion in the Brauer group can be identified with second Galois cohomology in the nth roots of unity. Okay, so the idea somehow is that the nth roots of unity, if I don't know how sophisticated your perspective is, the nth by mu n, you know, I suppose I mean the nth roots of unity in the separable closure, which would be the same as the nth roots of unity in the algebraic closure. But if the characteristic of K does not divide n, then mu n is defined that way. So if the characteristic does divide n, then there are going to be fewer than n. Mu n is going to have size smaller than n. And really, I mean, out of the side of my mouth at least, really what that means is that mu n is, viewing mu n as a Galois module is missing information. You should, in general, mu n should be viewed as a group scheme, and it is a Étale group scheme if and only if n is not divisible by the characteristic. What does it mean to be an Étale group scheme? It means you lose no information by plugging in the K-set points and viewing it as a Galois module. So there is a categorical equivalence between commutative Étale group schemes and Galois modules, and then whatever a non-Étale group scheme is, it's more than just plugging in the points over field extensions. Okay, so anyway, we're in the good case, and so why do you see that you're in the good case? Well, as long as n is not divisible by the characteristic of the field, then multiplication by taking the nth power is surjective on the separable closure. Okay, whereas, you know, if you were in characteristic P and you were not perfect, then multiplication by P would not be surjective on the separable closure. It would only be surjective on the algebraic closure. Okay, so you get this kind of map, and then if you take the Galois cohomology of this short exact sequence and you apply Hilbert 90, which is telling you that the multiplicative groups are going to, H1 of the multiplicative groups are going to be equal to 0. You know, I leave it to you, but all you have to do is write down the long exact cohomology sequence, and you will get this result. Okay, so the Brauer group is a torsion group, but the Brauer group is actually, you know, if you want it to be, you can understand it in terms of Galois cohomology with coefficients in these torsion finite modules, which are nth roots of unity. Okay, any questions? All right. For some reason that took a little bit longer than I was expecting it to. So now, now we go on with, I'm going to give you some examples of Brauer group computations. Again, I do emphasize it would be nice to have someone explain what the connection between this Brauer group defined as a Galois cohomology group is, the connection between that Brauer group and the Brauer group, which is classifying finite dimensional central division algebras over a field up to isomorphism. They're the same group, isomorphic groups. And so some things are actually easier to see on one side, or some things are easier to see on the other side. Okay, so let's compute the Brauer group of the real numbers. I claim it's Z mod 2. Okay, so I'll just say on the division algebra side, what am I saying? I'm saying that there are two finite dimensional division algebras over the real numbers whose center is equal to the real numbers. Well, the The obvious one, R itself, is what's representing the trivial element of the Brouwer group of any field. And since there's one more element, there must be one non-commutative finite dimensional division algebra over R. And that is this famous division, most famous division algebra of all time, Hamilton's quaternion algebra, which I'm sure you've probably seen. I'm just giving it some quaternion algebra notation. Okay. The unique 4-dimensional division algebra over the real numbers, non-commutative. Okay, so how do you prove this from our cohomological approach? Well, the Brouwer group is this is the definition of Galois cohomology, but the automorphism, the absolute Galois group of the real numbers, well, it's only 2 elements, right? So so we can use our cohomology, known cohomology of finite cyclic groups, okay? And so as we just did, every even dimensional cohomology group gets identified with the Tate H0. So what is Tate H0? Tate H0 is the invariance divided by the image of the norm map. And the module here is the multiplicative group of the complex numbers, because the complex numbers are an algebraic closure of the real numbers. Well, so the invariance of the complex numbers under complex conjugation, the real numbers, okay? And then we have the norm. And so the norm is famously, yeah, you know, it's literally just the complex absolute value in this case. It's a complex number times its complex conjugate. No, it isn't. It's the square of the complex absolute value. And so, you know, which real numbers are the absolute value of a complex number squared? Well, they're the positive ones, okay, among non-zero real numbers, right? So I took, you know, obviously the complex absolute value is non-negative, and then even yeah, I mean every positive number in the real numbers. Anyway, even if I just took the norm of a you know, of a real number, then that would give me its square, and every positive real number is a square, of course. Okay, so yeah, so the Brouwer group is the co-kernel of the norm map here. Okay. And so, all right, so it's the real numbers divided, non-zero real numbers divided by the positive real numbers, which is, I mean, by the way, this is actually the profinite completion of the multiplicative group of the real numbers. Why? Because the connected component of the identity of the real numbers is the positive real numbers, right? So this group has, the group of non-zero real numbers has 2 connected components, the positive ones and the negative ones. Anyway, so we get Z mod 2Z. Okay. All right, now I want to do that the Brouwer group of a finite field is 0. This is one of these results that, like, I like to prove this in multiple different ways. The lecture, now I'm realizing that I prepared a lot more than I needed to for this one lecture, but so later, I guess in the next lecture, I'll give you a fancier proof of this. Again, on the division algebra side, what is this saying? If you think about it for a little bit, it's equivalent to the statement that every finite division algebra is a field, okay, which is a famous theorem of Wedderburn. Okay, and so of course you can prove that in lots of ways. You can prove it. Basically, you can prove it using group theory. You can prove it. You can certainly prove it without using Galois cohomology. Okay, so what's our strategy here? Well, again, the Brouwer group, like any Galois cohomology group, is the limit of relative Galois cohomology of finite Galois extensions. Okay, and but now we know a bit more. Again, there was something funny with now all of these maps are injective. So this funny example of a direct limit of non-zero things being equal to 0, evidently that can only happen when the transition maps are not injective. That was the fine print. But what I just proved is that these inflation maps are injective, right? That's literally part of what I just proved. So if you think about it for a second, if you're trying to show that the Brouwer group of any field is finite, because these things are injectively inflating into the Brouwer group, it is necessary and sufficient to prove that each one of these things is 0. So for every finite Galois extension, so I think I just said that. Okay, so let's prove that. So now I want to show Again, of course, we know that the only finite degree Galois extension, every finite degree extension of a finite field is Galois, and there's a unique extension of every degree. We call it, we fix an algebraic closure, and we call the unique degree an extension fq to the n. Okay, so I want to show that this relative Galois cohomology group is equal to 0 no matter what n is. And what is the automorphism group? Well, the automorphism group is cyclic. It's generated by the Q power Frobenius. And now we do our stuff, right? We're in a situation where we're just computing H2 of some finite cyclic group. Well, that's Tate H0. Okay. Again, we know that the group, this cyclic group has a canonical generator given by the Frobenius. And so what should we do? We should take the Frobenius invariance of fq to the n, which is certainly fq cross, and then we should mod out by the image of the norm map. You know, just like we did before. Okay. Well, except now apparently, so if you think about it, this claim is reduced to the claim that the norm map on a finite extension of finite fields is surjective, okay, which is a well-known fact. Okay, so the norm map associated, the norm homomorphism on finite fields is, from attached to a finite degree extension of a finite field is surjective. You know, you can kind of push that statement around. And so again, for instance, if you, by the way, you see it's really equivalent, right? So you see that I proved that like the Brouwer group of a finite field is 0 if and only if this norm map is surjective. So if I ever prove, if in any way whatsoever, I prove that the Brouwer group of a finite field is 0, then I will have proved that the norm maps are surjective. But you can just do it. Like it's just an exercise in finite field arithmetic. Well, what is the norm map? The norm map is the product of the conjugates. It's a cyclic group. So each of the conjugates, or you just take various powers of your generator, right? So the various automorphisms are going to be identity, Frobenius map squared, all the way up to Frobenius map to the n-1. There you go. I see what to do. I can, this is x to the sum of 1 plus q plus ... plus q to the n-1. I see a finite geometric series. So the norm map, it's not that scary a map. The norm map from fq to the n cross to fq cross is just raising x to this power. So it's q to the n-1 divided by q minus 1. Okay, and so now you have your choice of how do you want to prove that every element of fq cross is of this form for some element of fq to the n. Well, when you have maps between finite groups and you're trying to wonder the size, knowing the size of the image is equivalent to knowing the size of the kernel. So let's look at the kernel of the norm map. The kernel of the norm map is the collection of these things such that raising to this power is equal to 1. All right, so what is that? That's, in other words, that's the corresponding number of roots of unity inside this finite field. Well, what is this? Well, evidently q to the n-1 divided by something divides q to the n-1, which is the size. So the roots of all the roots of unity in fq to the n has order q to the n-1. This guy visibly divides q to the n-1. And so the number of such roots of unity is q to the n-1 divided by q minus 1. Okay, so the kernel of the norm map has this size. We know what the domain is, and so therefore the size of the image is going to be this just by the fundamental isomorphism theorem for groups. It follows that the size of the image is going to be the size of the domain divided by the size of the kernel. There's the domain, q to the n-1. There's the size of the kernel. Lo and behold, we've checked that the size of the image is q minus 1. Okay, which of course is the size of fq star. Okay, so again, it's no problem to you can just, using nothing, it is an undergraduate level exercise to prove that the norm map is surjective on a finite extension of finite fields. Okay. Okay, so I mentioned that that is equivalent to Wedderburn's theorem. Yeah, and so let me quickly point at a generalization, and maybe I'll stop here. This would have been a more interesting problem if I hadn't stopped and talked all this stuff about cohomological dimensions. Now it should be, we'll see, maybe it will be clear what happens. And so if I look, what are these two cases that I just did, what do they have in common, right? I just computed the Brouwer group of the real numbers, and I computed the Brouwer group of a finite field. Well, in each case, all of our cohomology groups turned out, all of our relative cohomology turned out to be cohomology of finite cyclic groups, right? Which we have a formula for, so we were happy. What does that mean? It means that the absolute Galois group of both the real numbers and a finite field are procyclic groups. They're inverse limits of finite cyclic groups. Indeed, for both the real numbers or a finite field, every finite Galois extension is cyclic. Okay, so there's a generalization of this. What if I give you any field so that the absolute Galois group is procyclic? Again, procyclic literally means an inverse limit of finite cyclic groups. Here's a fact. It turns out that, okay, what groups are procyclic? I guess another exercise here is that a profinite group is procyclic if and only if it's a quotient of z hat. Okay, so that's, I'll write that down, exercise. G procyclic if and only if there exists n closed subgroup of z hat such that z hat mod n is isomorphic to G. Okay. Great. So all procyclic groups are precisely the ones that are, so z hat is kind of the universal procyclic group. It has every procyclic group as a finite quotient. That's fairly straightforward. But which procyclic groups can be the absolute Galois group of a field? That's what I'm asking now, okay? And my claim is that it's more restricted. Well, the trivial group can be the absolute Galois group of a field. That's the absolute Galois group of a field if and only if the field is separably closed. Z mod 2 can be the absolute Galois group of a field, evidently, because it's the absolute Galois group of R. My claim is that the other type of procyclic group that can be the absolute Galois group of a field is you take your favorite non-empty subset of the prime numbers, and you take the product of copies of ZP indexed by your set of primes. Okay, I claim, in fact, I claim there's going to be a algebraic extension of FQ, whose Galois group, just by Galois theory, you can see this. This slightly strange-looking Galois group is going to be the absolute Galois group of a algebraic extension of a finite field. And it's not obvious, but these are the only such procyclic groups that can be absolute Galois groups of a field. So you can't have, there's by a theorem of, one ingredient here is a theorem of Artin Schreier. So the only finite absolute Galois groups have order 1 and 2. That's a famous theorem of Artin Schreier. But like, why can't you have, I don't know, Z mod 2 cross Z5 or something? Okay, and so a reference for this is my most recent paper with Paul Pollack, reciprocity by resultant in K bracket T. We're in a situation of looking at procyclic absolute Galois groups, and so we don't really, we draw together some results from the literature that explains why this is true. Okay, so yeah, so these are the only procyclic absolute Galois groups, and so what happens to the Brouwer groups of fields with, so conversely, so these are the only procyclic Galois groups. Conversely, well, I've shown you every example. So this is the Galois group of any separately closed field. This is the Galois group of the real numbers, and this one is going to be the Galois group of a suitable algebraic extension of a finite field. Okay. So evidently, the Brouwer group of a separably closed field is trivial. It's Galois cohomology for the trivial group. It turns out part of Artin Schreier theory is a field has absolute Galois group size 2 precisely when it's real closed. So that's a field theory thing. You can consult my field theory notes. And so my claim is that in this case as well, the Brouwer group is Z mod 2 for any real closed field. And what does that come down to? It comes down to believing that the norm map, so there's a degree 2 algebraic closure. And so the claim is that the norm, the image of the norm is precisely the squares which have index 2 in the field. So this is really just checking whether you understand whether you know some basic stuff about real closed fields. And then the other claim is that as long as the absolute Galois group is infinite, okay, so it's a product of copies of ZP, I claim that the Brouwer group is going to be 0. Okay, so this is generalizing. We just did the case of a finite field where the Galois group was Z hat, which you guys finally told me was the product over ZP for all primes P. Okay, and so this is a generalization of the fact that the Brouwer group of a finite field is 0. I'm saying that the Brouwer group of any field whose absolute Galois group is a product of some ZPs for different primes P is going to be 0. And why is that? Well, what is the cohomological dimension of this guy? One. Because again, for the same reason that Z hat has cohomological dimension 1. And so there's a connection between vanishing of Brouwer groups and cohomological dimension 1, which Harari talks about. The case where, so I leave that as an exercise, or you can read about it in Harari. I recommend that you do the case where K is perfect first. That's easier. And what's the connection? As long as K is perfect, or maybe first do the case where K is characteristic 0, for instance, just to get started. If K has characteristic 0, then I think we can see it already, because then the n torsion in the Brouwer group for all n, oops, you're not looking at that, sorry. If K is characteristic 0, then the n torsion in the Brouwer group is this cohomology group. But hey, mu n is a torsion discrete Galois module, and so if you have a field of characteristic 0 of cohomological dimension 1, then yeah, all these groups have to be equal to 0. Okay, so that's getting you started. Okay, I think I'll just say one more thing, and then I'll end for today. I realized that when I went to do Artin Schreier theory, there was another moral that I didn't draw. So I mentioned that using this Artin Schreier isogeny in a field of characteristic P, so the map x goes to x to the P minus x is a isogeny on the surjective group homomorphism on the separable closure. Evidently, the kernel is the elements of FP, or can thought of as Z mod PZ. So this gives you your sequence. And then I took Galois cohomology, but I didn't draw. All I said was that meant that the first Galois cohomology group with coefficients in Z mod PZ was the co-kernel of the Artin Schreier map, was K modulo rho of K. But it's an exact sequence, and you keep going. And remember, this is the additive group, not the multiplicative group. So whereas for the multiplicative group, Hilbert 90 only tells you about the first cohomology vanishing. For the additive group, they all vanish. And so if you just record that, then you see that Galois cohomology with coefficients in Z mod PZ is going to vanish for all q greater than or equal to 2, which kind of relates back to what we were saying about cohomological dimensions of pro-P groups before. Okay, and so here's another exercise. I'll end with this. So suppose that you have a perfect field of positive characteristic, like a finite field, then automatically there's no p torsion or p primary torsion in the Brouwer group of the field. Okay. Yeah, so I think that's it for today. I was going to talk about C1 fields, and next time Harari gives a very funny, fancy proof of the fact that the Brouwer group of a C1 field is equal to 0. It's not the proof I'd seen before, but it amused me. So I'll remind you, I'll tell you what a C1 field is, and I'll prove it. And then the result that we're going for is actually computing the Brouwer group of a complete discrete valuation field. Which is really what we need in order to start doing local class field theory. So we're like pretty close to local class field theory now, or at least starting to talk about local class. Any final questions? Okay, well, I didn't keep you to 4, so we made it out okay. All right, have a good afternoon. Bye.
Bye.